Hi, welcome to the first video in my proof by induction differentiation series. Now, to begin with, let's have a look at the algorithm that we're going to use to tackle all proof by induction differentiation questions. So we're first going to do the base case, and we're going to assume like normal. We've seen this for all of our examples of proof by induction. Next, we're going to do the consideration step, and we're going to use the following trick. So with proof by induction for differentiation, we're usually going to be proving a formula for the nth derivative of a function. Now, when we do our consideration step, we consider n equals k plus 1, and we've assumed for n equals k. So we need to somehow relate the consideration and the assumption. So we consider n plus 1 or k plus 1, and then we can use the following trick. So the n plus 1th derivative is the same as the derivative of the nth derivative. So very similar to the summations trick and to the matrices trick that we saw before. We're basically going to rewrite the consideration as this. We can then replace the nth derivative with the assumption, and then all it's left to do is to do some rearrangements and do some tricky differentiation, potentially. Now, as before, really important to write a target, especially in these examples, because differentiation induction is going to require a lot of complicated rearrangements, which we're going to see. But anyway, let's get cracking. So base case, that's going to be the first derivative. So for n equals 1. So n equals 1, we're doing the first derivative of this function. Now this is a chain rule derivative, but you could also do it by the quotient rule. I prefer the chain rule. So this is 1 minus x to the minus 1. So we do the derivative of the outside, which is minus 1 to the minus 2. We put the inside back in, and we multiply by the derivative of the inside. This becomes 1 minus x to the minus 2. And well, if we look at what we're kind of targeting here, we're looking for 1 factorial over 1 minus x to the 1 plus 1. Well, this is a negative power, so this can be written as 1 minus x squared, and 1 goes on top. And well, this is in fact equal to 1 factorial over 1 minus x to the 1 plus 1. So we get it as true for base case. Now, in comparison to previous induction methods, you'll see that this base case is a slightly longer, quite a bit longer than these previous examples, and that's what makes proof by induction differentiation hard. We're going to have longer rearrangements, longer for each step. This example is not too bad, to be honest. We'll have a look at a much more complicated example in future videos. Alright, now we do our assumption. So assume true for n equals k, i.e. the kth derivative of 1 over 1 minus x is equal to k factorial over 1 minus x to k plus 1. So as always, we're just replacing k with n. Next, we're going to consider n equals k plus 1. So we're considering the k plus 1th derivative of our function. But well, this is the same as the derivative of the kth derivative. But that's in our assumption. So we're talking about the derivative of this. Now, before we even write down our target, we might want to just continue on with this pattern where we're just going to differentiate it, get rid of the derivatives, because clearly our right side of the target is not going to have a derivative. So we might as well differentiate it anyway. So k factorial is a constant, so I can bring it outside of the derivative. I'm going to rewrite the fraction as a power. So I'm going to have 1 minus x to the minus k minus 1. And like we saw at the top, this is just a simple chain rule derivative. So derivative of the outside, which is minus k minus 1, something to the power of this power minus 1, so minus k minus 2, and then we put the inside back in, and we multiply by the derivative inside. We can cancel out the negatives, giving us k factorial times k plus 1 times 1 minus x to the minus k minus 2. Now you might be able to see straight away what to get to. This example is not too bad. Now our target, which I'm going to just write down on the side here, our target is if I was to replace k plus 1 in our expression on top there. So k plus 1 factorial over 1 minus x to the k plus 2. Now clearly by converting this to a fraction, we're going to get the 1 minus x to k plus 2. So we get something over 1 minus x to k plus 2. And in fact, we've seen in previous videos when we dealt with a factorial, I think in our inequality video, factorial is saying 1 times 2 times 3 times 4 times 5 all the way up to k. So if I want k plus 1 factorial, it's k plus 1 times k minus 1 times k minus 2, etc. So this expression here is k plus 1 factorial. And well, that's exactly what our target is. So as true for n equals k plus 1, when true for n equals k, and true for base case, n equals 1, by mathematical induction, it must be true for all n greater than or equal to 1. And we're done. So reasonably difficult example, but it's not the most complicated that we can sort of expect from this type of induction. I hope this has been helpful, and I will see you in the next video.